Hello, everybody. I hope all of you are doing well. So, we're going to be looking at actually probably what I think is real statics from now on. We're going to be looking at the idea of rigid body equilibrium. Okay, and then I'm going to outline a basic procedure. We will keep this video short, and then we will just go on and dig into the buffet by looking at problems. Okay, I hope that sounds good to you. All right. So, rigid body equilibrium, that's the topic for today. All right. So, what is the concept of equilibrium? Okay, so equilibrium implies the following. So, equilibrium implies that, and when we say equilibrium, we mean static equilibrium. Okay, so static equilibrium implies that the body has not undergone any translation. So, which means that there is no translation. Okay, which implies that the net force on the body is equal to 0. Okay, so this implies that the sum of all the forces acting on the rigid body is equal to 0. Okay, and of course, first of all, we know what is meant by rigid body, right? So let me maybe write it out. So rigid body, it does not show large deformation when subjected to forces. Okay, so rigid body no large changes, no large shape or size changes. Okay, this is of course a big white lie because that's not the case for anybody, right? I mean, there is nothing called as a rigid body in a sense. Every body, if you apply some force, is going to deform in some small way. But what we are saying is, okay, hey, let us say that the deformation is not too large, okay, such that it's not something that is visible to our naked eyes. Okay, so then we say, okay, what is the concept of equilibrium? It means there is first of all no translation. The second thing is no rotation. Okay, which implies that the net moment, okay, or the sum of all moments due to the forces and due to couple moments, okay, due to forces and couple moments. Let me maybe scoot it a little to this side so that I can write out my couple moments. Okay, apologies, couple moments acting on the body at an arbitrary point. Okay, so sum of all the moments at an arbitrary point, at any point on the body, arbitrary point on the body is equal to 0. Okay, all right, so this is the meaning of a body having no rotation whatsoever, which means that both of these can be written in the form of an equation. Okay, so this no translation implies that the net, the summation sign, so the net force acting on the body is equal to 0. Okay, and then the no rotation implies that the net moment acting at any arbitrary point is equal to 0. Okay, so here in this situation, this is any arbitrary point O on the body. Okay, so this is the mathematical statement of being in equilibrium. Okay, Let me underline these two because these are the equations that we're going to be riffing off of. Okay, all right. Now I come to the basic procedure of how to proceed with rigid body equilibrium. Okay, so let's go to the basic procedure. So basic procedure to solve problems. This is very important that we follow each and every one of these things that I'm outlining here, and let me outline the procedure for 2D, and then we will extend this for 3D as well. Okay, so I will outline the procedure for 2D problems, and we shall extend that to 3D problems as well. Okay, all right, so here are the steps that we need to take to solve the problem. First step, set up a coordinate frame. Okay, so set up a Cartesian coordinate frame, and this is something that I will draw at for each and every problem. Okay, so here is my coordinate frame. So look at the way I'm drawing it. Okay, so here is my x-axis and y-axis, and I'm going to point out something else that is a little new to us. Okay, I'm going to say that, okay, hey, all of the rotations that are counterclockwise are also positive. Okay, so what is the meaning of this? So this figure implies the following. Okay, implies that A, all forces pointing to the right are positive. All forces pointing up, they will be taken as a positive sign, and then all rotations that are counterclockwise, or all moments that are counterclockwise, I sometimes interchange it and write that all moments that are CCW, they will be treated as positive. Any force and moment that is pointing in the opposite direction will be negative. Okay, so any force or moment in the opposite direction to what we have just described now will be negative. Okay, so this is the meaning of this figure. Okay, and this is very important that we keep drawing it for each and every problem. Okay, so the things that are shown here is all the forces pointing to the right are positive, which means pointing in the positive x-axis. All the forces pointing in the positive y-axis are positive. All the moments that are counterclockwise are positive, and any force or moment that is in the opposite direction, they will be taken as negative. Okay, those did not come out as straight lines, so let me try again. All right, and one more time. All right. Okay, so this is the first step. The second step is the next important step. Okay, is the following. So B, draw a free body diagram from now on FBD of the rigid body okay, this is the next step. Okay, so first of all, you know what is a free body diagram, and then what am I supposed to draw on the free body diagram. Okay, here are the questions. Okay, so what is an FBD? And what do we mark or draw? Okay, let me write that properly. Mark or draw on the FBD. Okay, so let me define that. Okay, so free body diagram, okay, is the following. It is an isolated or a floating rigid body, okay, where you have removed the rigid body from everything that holds it in place. Okay, so this is a floating representation of the actual body drawn after detaching the body from all the constraints that held it in place. Okay, so this is the first thing. What is a free body diagram? The second thing is, okay, what do I mark on the free body diagram? So on the FBD, we draw or mark the following. And once we draw figures, you will understand what I'm talking about. Okay, so on the FBD, we draw or mark the following. Okay, so what are the following? First thing is you draw all the applied forces and applied couple moments acting on it. Okay, so mark all the applied forces and applied couple moments acting on the body. Okay, then comes the important thing. You mark all the support reactions on the body. Okay, so mark all support reactions on the body. Okay, so which obviously leads to the next automatic question, what on earth is a support reaction? Okay, so typically when you look at bodies are supported by many ways. Okay, so typically bodies are held in place by supports or restraints. Okay, these could be, there are several types of supports that we're going to be seeing, but for maybe if I want to make a list of them, for example, I could have a pin support, I could have a rocker or a roller support, I could fix the entire body, I could have cables supporting the body. Okay, among other things, these are the different types of supports that we typically see. So typically bodies are held in place by the supports. So when you draw the free body diagram, you do not draw the support, but you draw the effect of the support. Okay, so which means that when we draw the FBD, okay, and of course these are all the different types of supports that I wanted to mention here. So when we draw the FBD, we do not draw the actual support, but rather we draw the effect of such a support on the body. I hope this makes sense to everybody. And of course, once we solve some problems, you will also see that, okay, this makes a little more sense. Okay, So typically when we draw the free body diagram, we do not draw the actual support. So this is something very important. So when you draw the free body diagram, you do not draw the actual support. But what do you do? But rather, we draw the effect of such a support on the body. Okay? And so this is in the form of a support reaction. Okay, so this is in the form of a support reaction. This effect of a support on body, this is called as a support reaction. Okay, and there are two types. Okay, so let me, two broad categories of support reactions. Okay, so here are two foundational statements or fundamental statements. So important statement on support reactions. Okay, this is something that you may want to remember for the rest of this course and for any other course. Okay, here is the statement. So A, if a support prevents translation in any direction, then on the free body diagram, this is represented as a reaction force along that direction. And the second statement, so I'm going to take these statements and bring them onto the next page, okay, so that they have their own importance here. So I'm going to cut that, or probably, cut that. I did not mean to copy it. So I'm going to cut this off, okay, and in the manner of cutting things off, I lost some information here. So I'm going to paste that down here, okay. So this is the important statement on support reactions. I don't need that guy there. So that's the first statement, okay. Then the second statement, if a support prevents or resists, let me write my prevents properly, or resists a rotation about a certain direction, then on the free body diagram, this is represented as a couple moment or a reaction moment about that direction, which could be a line or an axis. Okay, so two foundational statements which I'm going to read once again because this is very important that we understand. If a support prevents translation in any direction, then on the free body diagram, this is represented as a reaction force along that direction. Next statement, if a support prevents or resists a rotation about a certain direction, then on the free body diagram, this is represented as a couple moment about that direction. Okay, and let me call these as 1 and 2 because I was using little a, little b, and little c for the steps taken. Okay, so this is 1, this is 2. Okay, then I go to step C. So after setting up the coordinate system, and drawing, and after drawing the free body diagram, we use the equations of equilibrium. Okay, what are the equations of equilibrium? Okay, so first of all, let me maybe redraw my x and y directions, because I want to show you something that I'm going to be consistently following. Okay, so this is positive x, this is positive y, and then this is the counterclockwise ascents for the positive moment. Then here is what I'm going to say. Okay, the first equation is the net force, the resultant force is equal to 0. Okay, now because I'm doing this problem in 2 dimensions, I'm going to have forces in x direction and y direction. So this statement is equivalent to the following. Okay, so this is equivalent to saying, if I take all the forces acting in the x direction with the forces pointing to the right being positive, I will be able to set them to 0. And then if I take all the forces which are acting in the y direction with the forces pointing upwards, this will be equal to 0. Okay, so these two are equivalent. Okay, so this is the same as saying that the net force is equal to 0. The same as saying that this net force is equal to 0. So I guess I want to make some space for this. So hang on a minute. I think I can squeeze this guy in here. All right. Okay. This is the same as saying that. Okay. So that's something that we are going to be using. Instead of saying net force is equal to 0, I'm just going to say, okay, sum of all the forces in the x direction is equal to 0. All the forces that are pointing to the right are taken as positive. Look at that, the plus sign here, as you can see. Okay, and then I will say that, okay, similarly, I will say that all the forces which are pointing upwards are positive, and if I sum up all of those forces, then I should be getting the sum of all the forces in the y direction to be equal to 0. Okay, so this is the first equation of equilibrium. The second equation of equilibrium is that the net moment about any arbitrary point on the body will be set to 0. And look at this, because I'm trying to do it from a 2-dimensional perspective, so I'm using it in 2D. So let me make that statement here. So this is 2 dimensions. If I'm making the statement where I'm saying the net moment is 0, then I'm going to draw a small swirly arrow here which says that, okay, hey, all the moments that are counterclockwise are taken to be positive. Okay, so that's something that also is true. Okay, so all the moments that are counterclockwise are going to be taken as positive, as you can see from what I'm trying to draw here. Okay, and this is the same as saying the net moment is equal to 0 at any point O. Okay, so O is an arbitrary point here. Okay, so this is any arbitrary point. Okay, so which means that in 2D, here are the equations of equilibrium. Okay, so in general, so which means in 2D, the equations of equilibrium are, okay, I'm going to take these two guys from here. Okay, this implies no translation. Okay, and then I'm going to have one more equation coming from here. This implies that there is no rotation of any kind. Okay, so which means that I'm going to have a total of 3 equations. Total of 3 equations in 2D problems. Okay, so which means that if I'm trying to solve a problem in 2D, then I cannot have more than 3 unknowns. Okay, so which means that since in 2D we have only 3 equations of equilibrium, then cannot have more than 3 unknown quantities to solve for. Okay, and if I extend this to 3 dimensions, right? So in 3D, the equations of equilibrium will become the following. Okay, so they will be sum of all the forces in the x direction is equal to 0. So let me assume a coordinate frame here. Okay, so this is not straight yet, so let me say this is the x-axis, the y-axis, and the z-axis. Okay, so this is in 3D, so this is x, this is y, and then this is z. So sum of all the forces in the positive x direction is 0. Sum of all the forces along the positive y direction is going to be 0. This is in 3D. Then sum of all the forces in the positive z direction is going to be 0. And then I'm going to have 3 moment equations. Sum of all the moments about the x-axis is equal to 0. Okay, so here is typically how I do it. I say, okay, hey, I'm going to sum moments about the x-axis. All the moments that are counterclockwise about the x-axis are taken to be positive. Okay, then likewise I'm going to say, okay, sum of all the moments along the y-axis is 0, so which means that all the moments that are counterclockwise with respect to the y-axis are taken to be positive. And then lastly, I'm going to have sum of all the moments about the z direction is equal to 0, which means that all the moments that are pointing vertically up will be treated as positive. Okay, so let me mark that a little better. This did not come out too great, so let me redraw that. So this is the well, that's too long, right? Either too long or too short. Okay, so that was not good either. Okay, so now I think I'm better. Okay, so this is the double arrow here. Okay, so in 3D I have 6 equations. Okay, so in 3D, so this is in 3D, these are the equations of equilibrium. Okay, this was in 2D, the equations of equilibrium, as we have just written there. So in 3D problems, we have 6 equations of equilibrium, which means that we cannot have more than 6 unknowns to solve for in 3D. Okay, so this about wraps up the basic procedure for solving problems in rigid body equilibrium. So let me just very briefly go back and give you a summary of what I'm doing here. So when we say equilibrium, there is no translation, there is no rotation. If there is no translation, then the net force on the body is going to be 0. Okay, so you can say this is the net force on the body. Okay, and then you can also say that the net moment about any point O is going to be equal to 0. Okay, this is the basic idea of equilibrium. What is the procedure? I set up a coordinate frame. Positive x-axis, positive y-axis, counterclockwise rotations are positive. Then I draw a free body diagram. What is a free body diagram? It is a representation of the actual body but without any constraints holding it in place. Then on the free body diagram, you mark the following. You mark all the applied forces and couple moments, and then you label the dimension. That is also important. I will sneak the statement in. Label all dimensions. Okay, this is an important statement. Okay, so you need to label all the dimensions. You mark all the applied forces on the body, you mark all the applied couple moments on the body. Okay, and then you mark all the support reactions. different types of supports. We're going to see some problems on these. Okay, basic idea of a support is it's a restraint on the body, but instead of drawing the actual support, you draw the effect of the support on the body when you're looking at the free body diagram. And two statements on the support. If a support prevents translation, then you mark a reaction force along that direction. Okay, so you mark a reaction force along that direction. If a support prevents or resists rotation, you mark a reaction moment about that particular direction. Then once you set up your coordinate frame and free body diagram, you just go and say, okay, if this is a two-dimensional problem, I'm going to have three equations of equilibrium, as you can see here. But if it's a three-dimensional problem, I do the same thing. I set up a coordinate frame, positive x, positive y, positive z, and then I can say, okay, I have 6 equations of equilibrium in 3D, which means I can solve for only 6 unknowns in 3D. In 2D, I can solve for a maximum of only 3 unknown quantities. All right. Thank you for your patience, and we will solve some problems on rigid body equilibrium. Bye-bye.